Efficiency. It's how much bang you get for your buck if you want a non-sciencey definition. It's how much of the energy that we're supplying or the power that we're supplying goes into work or power, and how much of it is wasted as heat and sound and other. The symbol for efficiency, there's two. For years, I just wrote out EFF for efficiency, and it was only a few years ago that I learned there is a Greek letter for efficiency. It's like a lowercase n with a droopy tail. It's the Greek letter eta, for those of you who speak Greek. Efficiency. So if you want to have a nerd fest and write the little Greek letter eta, you can. If you just write efficiency or EFF, I'll figure it out, because that's what I still tend to do if I don't think about it. It's a habit. What are the units? Percent? How do we calculate efficiency? Efficiency is the work you get out divided by the work you put in. Or the energy you get out divided by the energy you put in. Or the power you get out divided by the power you put in. This will give you a decimal, and then you multiply by 100 to get a percent, the same way you do for your tests. And that's really, if you know how to figure out what your percent is on a test, it's the same math. What's the test out of? 80. What'd you get? 75. How do you make that a percentage? 75 divided by 80 times 100%. What's the energy out of? And I know it says out on the top. It's an unfortunate linguistic error. How much energy did what was it out of grand total? How much did we actually achieve? That's the answer. Now, I have a real problem with this, not just because in English the word out seems to be in the wrong place, but there are times when just the way the question is phrased, the word out happens to appear right next to the, for example, power in. What do you call this white thing to my left here? An outlet. You plug in an outlet. The power coming into my computer is coming from an outlet, and it gets confusing. So here's Mr. Dewick's dumber, simpler version. We live in a universe where you can't get free energy. So if you want the simpler version, it's always going to be the smaller number divided by the bigger number. You can't be more than 100% efficient. Now, if you actually are, you'll win a Nobel Prize, and probably in 3 or 4 years, you'll be able to buy and sell Bill Gates. You'll be the wealthiest person on the planet because you would have created free energy. And if we have free energy, just even with our current level of technology, we can pretty much engineer our way out of any of the world's problems if we had free, unlimited, clean energy. And please try to invent free, unlimited, clean energy, but you'd be violating a universal law that we'll be talking about in a couple lessons. The only risk with this, make sure the units match. In other words, please don't divide joules by watts. It's got to be watts over watts or joules over joules. Thank you very much. But then it's going to be always the smaller number divided by the bigger number. So that's why I wrote efficiency is always less than 100% unless you plan on winning a Nobel Prize. If you've ever heard the term perpetual motion machine, that's the term that we used to refer to a machine that is more than 100% efficient. It's impossible. Sierra's eyes are gleaming. She's got the wheels turning. Well, what if you... No, it's impossible. But what if you added some... No, it's impossible. So, a typical household light bulb transforms energy at the rate of 60 watts. That's your standard bulb. Most of the energy goes into heat instead of light. Of that 60 joules per second, because that's what a watt is, 57 joules per second goes into heat, and only about 3 joules per second goes into light. So an incandescent light bulb, not very efficient, only about 5% efficient. And you may have noticed that if you ever touched up a bulb after it's been on for a while. You burn yourself, that's wasted energy. A kettle might transform electrical energy into heat at the rate of 1500 watts, and the power rating of an electrical appliance is usually printed somewhere on the appliance. Okay. Let's crunch some numbers here. Let's lift something with a motor. Oh, do me a favor. Underline the word lift. Whenever I'm talking about lifting something, who remembers what's our work equation going to be? It's going to end up being mgh, and we'll derive it, but that's one if you want to make a little back pocket note or a little back of the book note. Lifting, if you're talking about how much work, it's mgh. Okay. So A says, find the work done. Brian, this is your cue. Work equals what times, I think it was you last time that I picked on. Work equals what times what? Okay. So we would start out by saying, I know that work equals force times distance. Oh, it's also the area under a force versus distance graph. Do you see a graph here? Captain Obvious, don't use that. When you lift something, which force are we doing work against? And that's where the mg comes from. Get the obvious one, in other words, yes. And then this is why because it's a vertical distance, we chose to call that height. What other thing in this same section is mgh? It's also on your formula sheet if you look. There's something else that's mgh specifically. It says something equals mgh. I think, isn't there? Phys ed? No. That's going to become potential energy. And we're going to talk, you may have noticed, I've been using joules and energy interchangeably. You're going to learn in a couple of days, Jacqueline, energy is the ability to do work. So if you have energy, you can apply a force over a distance. And there's many different ways to store energy. One is lift something in the air, you've stored energy, because if you let it go when it hits the ground, will it apply a force over a distance, especially if your head's down there? Yeah. Okay. Brian, what's the mass here? G. Do I need to put the negative in? Nope. Works a scalar. H Cole. I saw that big long blink. H Cole, what's the height? $12.5, you said? How many joules of work is this motor going to do? And it's going to do this much work no matter what, whether we go really fast or really slow. This is how much work it's going to do. So that's going to be 255 times 9.8 times 12.5. You'll get 31,237.5. I'm going to write down 31,200, but I'll keep this on my calculator. Work. What are the units for work? Is work measured in watts? No. Don't put the 2W at joules. Okay. Cool. Oliver, what's B want me to find? I think you were the one that I went to with this last time too. What's B want me to find? And what was the equation for power? It's on your sheet if you have it handy or if you have it next to you. So power is P, capital P. P equals, that's momentum, capital P, not lowercase p. And it's not your fault. I've gone on my rant how we're running out of letters in the English language. And okay, so a little further down, is it down or above? I think it's above. Oh, above momentum, because I used to do energy first. Yes. W is work, T is time. And Oliver, my friend, how much work? Look up. Our answer from A, which I have on my calculator. I'm going to write 31,200, but you know I'm using my answer button. Yes? And Oliver, read the question. How much time? I think you're right. I didn't hear. 4.0. Yeah, 4. Yep. It's pretty fast. Well, 12.5 meters. How high is that? About 4 stories. Ish. 1 story is around 3 point something meters. So 3 times 4 is 12. 3 point something times 4 would be 12 point something ish. So lifting that's about a story a second. That's pretty fast. Do you all get 7,809 point? I'm going to call that 7, 8, 10. I'll go to 3 sig figs. Oliver, ready for the dumb joke? Are you ready? Are you ready? Power is measured in watt? Power is measured in watt? Oh, you missed that punchline there, my friend. You're better than that. Okay. And now we get to the new part. Hannah, what's part C wanting me to find? Efficiency is going to be... Now I pause. I notice this question gave me power. So I think it's going to be power out divided by power in. You know what? That number right there is power. That number right there is power. It's going to be the smaller number divided by the bigger number. Which of these two is the smaller number? And of course, you know I'm going to use my answer button, but I'll write that. And then 12 kilowatts. What's 1 kilowatt? 1,000. So 12 kilowatts is... And then if you want to make it a percentage, because this will give you a decimal. So this number divided by 12,000. And so this motor printed on the side of it, it would say it was a 12,000 watt motor. Or if, would you get 65.1? Or, to be honest, instead of watts, it would be in horsepower. It's a 16 horsepower motor. That's where I cook these numbers up from. Okay, so this 16 horsepower motor, how efficient was this motor? You know what? This is probably not a gasoline motor, because gasoline internal combustion engines are terribly inefficient. Can you hear a gasoline engine from a long distance away? Do they give off also a lot of heat? Yeah, that's a lot of wasted energy. That sound energy and that heat energy. Electric motors are way more efficient. They can get warm too, but nowhere near like a gasoline engine. Got 4 questions? Yeah, we're good. Girl pushes a... You know what? 3 times 10 to the 2, that's 300, which is less writing on my calculator. Newton, did they give me the mass? When they tell me something is newtons, what are they giving me? I'm looking forward being the letter W. Don't say work. No, now. Wait, no, now. Yeah, they're giving me mg there. Can I figure out the mass? I can divide by 9.8 if I need to. But if I'm using mg in the question, I'll just plug in 300 for the mg. So a girl pushes a 300 Newton box along the floor for a distance of 4 meters. Friction is 0.33. She then lifts the box straight up. So if I'm visualizing this, I guess she pushes it, and then she lifts it. I'm going to argue, Tristan, I think this has 2 parts. I think part A, when it says find the minimum amount of work, I think it's going to be the work done pushing and then the work done lifting. Is that okay, Sierra? Why did I say minimum amount of work? You'll see why in a second. Brian, your cue, work is what times what? Force times distance. So I think work pushing is going to be force pushing times distance pushing. And I think work lifting is going to be force lifting times distance lifting. In fact, you know what? This here is going to be, don't write this down, but it's going to become MGH. So that one I got. The pushing one. How hard is she pushing with? What force is she pushing with? Is she pushing with 300? What direction is that 300? If it's weight, if it's mg, down. That's not the pushing force. And by the way, Cole, who said, yeah, what else did this question give me that I haven't used yet? This is a job for a free body diagram. Here's the box. While she's pushing, what are the forces acting on it, Cole? Get the obvious one. Is the box sinking into the ground like quicksand? Is it flying here like Superman? I think I can safely say this. That force there, which I've often called applied, I'll call it push to go with work push. How big does it have to be if this thing is going to move? What does it have to cancel out? And this is why I said minimum. She might be pushing hard enough to even have extra force canceling out friction, but let's assume she's going at a constant speed. She is exactly and only, Christy, canceling out friction. That's it. So I'm going to argue that the work done by pushing is going to be, you know what? I don't want to write, let's do this. Draw a little arrow pointing that way. What did you say work was, Brian? So it's going to be force, push, times D, push. And this one, MGH. We've done that one enough. Hopefully that one's not a big stretch. And I've just showed you where it's sort of hidden on your formula sheet, described as something else. How big is force push? Would you say it's the same size as, Cole? You're right. Oh, I thought you... No. What does the force push have to cancel out? What does it have to be the same size as? Gotta be. Or bigger, but this is why I said minimum. All right. Friction is what times what? I don't know the normal force. Oh, but look. Another force the same size as the normal force. Which force is the same size as the normal force? Weight. No, now. Weight. No, now. You follow those steps? Is that okay, Nick? So I'm going to do that in one thought process. If you want to write down more, you can. But Nick, I'm going to say, okay, this is going to be mu mg times d push plus mgh. Hey, Nick, what's mu? I don't know. What's mu with you? What's mu? Okay. Do I know the mass in kilograms, Nick? Say no. But do I know mg in newtons? Say yes. What was the weight? Oh, I like that. What's the distance that we pushed? What you say when you golf? Plus? Do I know mgh? Do I know m? Say no. Oh, but do I know mg? What was that? Do I know MG? What? Do I know MG? Yeah! You just told me 30 seconds ago with confidence in your voice. I said, do I know MG? And you yawned. Yeah, 300. Do I still know MG? Yeah, it hasn't changed. You with me? Because that was a little silly, right? Right. I didn't give you the mass. I gave you the weight. No, now. What was the height? What's the minimum amount of work she's done? Tristan? 756? This is work. Work is not measured in watts. Units for work. Now that would be if her muscles were 100% efficient, her body would have lost 756 joules of food energy, and that would have gone into pushing this object. How much food energy did her body use according to part B? I've just scrolled down. What does part B tell me? How much food energy did she use? How efficient is this? Well, efficiency is going to be the smaller number divided by the bigger number. It's going to be the work out divided by the work in. The food that she ate, the in, was 1,200. How much work did she get out? 700. Is it 756 even?
Yeah.
Nice. That's a fluke, but I'll take it. Oh, and then times 100 to make it a percentage. So 756 divided by 1,200. By the way, I can make that 0.63 into 63% in my head, and if you can skip typing the times 100 on your calculator. In fact, you can even skip writing the times 100. I'll clue in that you've done the math in your head, and if you're comfortable enough with percentages, good. 63% efficient? Where'd the other 37% of the energy go? Probably heat, because we sweat. Is that okay, Michael? Yeah? Was there a part C? No. Also some nice review of forces. We're getting towards the end of the year. This is May the 4th. Stair climbers are great examples of both work and power and efficiency. Their work in that you use energy, their power in that the faster you climb those stairs, the more tired you get. And you can figure out some efficiency. Oh, I didn't do efficiency. Oh, I did. Let's see. Cool. On a stair climber at the gym, a 58-kilogram person lifts. I underline the word lift. Right away I'm thinking if I'm doing any work for lifting, it's going to be MGH. Their center of mass up 18 centimeters. Nice try. Cross out the 18 centimeters. How many meters? I'll give you a hint. 0.18. And this is what I often do to make sure I don't foolishly use the wrong units. As I read the question, Oliver, I'll cross out yucky units and just fix them to the ones that I want. I think I've used the phrase lazy and organized, right? They take 500 steps in 10 minutes. Nice try. 10 minutes? No. In your head, how many seconds is 10 minutes? 600? And their muscles are 20% efficient. Okay, I've got my units happy. Jacqueline, what's A want me to find? What the heck is the rate at which the person does work? What's that? Power is the rate at which work is done. Jacqueline, what's part A asking me to find when it says the rate at which the person does work? Power, you say? Really? Okay. Oliver, what's the power equation? Yeah. Oh, Jacqueline, we're lifting, so what's our work equation going to be for the lifting portion? Hey, there you go. Geez, this might be pretty straightforward. Let's see. Jacqueline, did they give me the mass of this person? By the way, if the mass was bigger, would power be bigger, smaller, or would it stay the same? So looking at this equation right here, as m gets bigger, what happens to our answer? This is why heavier people have a tougher time exercising, because they get tireder quicker. That's why little kids can run around forever. Right? You look at little kids and my goodness, they've been on that playground for 5 straight. Maybe you guys are still at that blessed stage, and glory be to you. But you'll suddenly find when you're in your mid to late 20s and 30s, holy smokes, stuff that I used to be able to do for hours, I got to work at. No pun intended, not work the physics way, work the I'm getting tired way. G, Jacqueline? H? No. 0.18 is incorrect. I'll pause and see if anyone can see it. What? Times what? Because how many steps is this person taking? Okay, so the height that they are climbing, and this is how a stair climber works. You don't actually go anywhere, but you are still climbing a height. I like this question. Oh, time? Okay, and I will feel okay to give you a time in minutes or hours, because that's still common units. And I will feel okay giving you the occasional distance in centimeters. That's a fair conversion for me to expect you to do. I might even once in a while give you a mass in grams, because those are all unit conversions, Tristan, that we've done. What do you get? I don't even know. Sorry? I'd be surprised if this works out evenly, but maybe it does. Times 0.18 times 500 divided by this. Actually, this might 85 point. You know what? Let's carry everything, because we're going to use this, I bet you, for part B. So you know what? I'll write 85.6 equals 85.3. 0.26. That equals 85.3 units. Work. Power is measured in watt. Watts. Okay. What's the letter that we use for work? What's the variable that we use to represent work? W. Stupid way to remember that it's in joules. Remove half the W. What letter is sitting there? There's your joule. If you're looking for a dumb way to remember this, okay, half a W is a J. Sort of. I mean, come up with your own stupid ways to keep units straight, but whatever works, right? Okay, if you make it like that, I know it doesn't work, then it's a check mark, but whatever. Fine. Sierra, let's do B together. Oh, we're finding power. I'm sorry. You're right, and I'm wrong. How often does that happen? Shut up. I saw some of you counting already, right? Carry the one. There's probably a squared in there. Jacqueline, you're right. It is watts. And oh boy, am I going to put this lesson on YouTube? And you know what's really sad is on Thursday, right now, my students are watching this lesson next week Thursday in my Block Gs, and they're realizing that their teacher is a total meathead. So whoever my TOC is this Thursday right now, my students are all going to be watching this lesson, and they're in class giggling away, thinking bad thoughts about me. I know who you are. Okay. Sierra, let's do B together. What does B want me to find? Isn't that power? Didn't we just find it? Well, this was how much power we got out. We want to figure out how much power this person had to take in to get that out. What else has this question given me that we haven't used yet? That 20%. That 20%. So efficiency is going to be, ready? Now you can also think this, I think. Efficiency is power, what did I say? Out divided by power, what did I say? In? I think the power out is that number there. I think we want to find that. Where is that number right now? On the... Bleh. Oh, no. In fact, we did this last day with T, time. We said, you know what? You can multiply that by power in and divide that down there. Is that okay? Hopefully now I've really convinced you why I say Please don't memorize equations. We can derive them. So apparently, yet another way to calculate power in, if I know the efficiency, is to go power out, 85.26 divided by 0.2. How many of you ever worked on a workout machine like a exercise bike or an elliptical or whatever? Okay, many of them have calorie trackers that you like. Sometimes even have a little thing you clip to your finger that supposedly gets your pulse, and it tries to tell you how many calories you burn. They're total garbage. Unless they know what your body's efficiency is, they have no idea how many calories you actually burned. They can only measure the number of calories that you output to the machine, which is very different. Someone who's in phenomenal shape, whose body is much more efficient, will burn far fewer calories than someone who's really out of shape doing exactly the same exercise. So just letting you know, there's some garbage science going on there. What do you get? 426.3. Jacqueline, power is measured in what? Yeah, I'm sorry. You know what? I'm going to put that on YouTube, this video, just to remind myself to be humble. So all the kids that look at my stuff online know that this idiot teacher sometimes is just totally out of it. Okay? Last one. Remember that motor that we found the efficiency of earlier where it was like 65% or something like that? And I said to you, I'm pretty sure it's not an internal combustion. Gas engines are usually around 20%-ish, give or take, efficient. So this one's 18% efficient. Only 18% of the chemical energy. Where do gasoline engines, this is meant to be stupidly obvious, get their chemical energy from gasoline, okay? From the explosion and chemical bonds and all that. Combustion. So only 18% of the chemical energy that's used to operate the motor is converted into forward motion. The rest goes into heat and sound and yucky waste. Okay. Suppose we have a 200 horsepower motor. Tristan, what's A want me to find? Okay, now this is not, I'm not going to go power equals work over time. I think what they want me to do is convert 200 horsepower, because that's an imperial unit, to whenever I convert something, what was the first thing I said I always do as a no-brainer before I even start? Write down what they? Yeah, sure. So you're telling me I'm going to write down 200 HP? I'm trying to remember if you were the one that I picked on last time too. Maybe not. Oh, where do I want horsepower to be in the conversion factor if I want it to cancel? On the... And watts is going to be on the, and I guess the 750, according to the conversion factor in brackets, goes with the watts, and the 1 goes down there. Where is that 750? On the top or on the bottom? So I'm going to times by 750 or divide by 750. And I don't bother memorizing it. I just let the units tell me. So 200 times 750, what do you get? How many watts is this gasoline engine? Sorry? So, by the way, one advantage of horsepower, it's a smaller unit and gives us numbers easier to wrap our brain around, because 150,000 is a big enough number. I don't know. Okay. Cool. Chloe, what's B want me to find?
How much motion energy?
In what? Motion energy in? No, motion energy in?
Oh, in joules.
In joules. Oh, work. Joules. What's the power equation?
Power equals work.
You know what? Get the work by itself.
Work equals power times...
Okay. I'm going with this. I could probably, Brian, try force times distance, except I see neither a force nor a distance anywhere in this question. So why don't I use my answer from part A, which was power? You've seen that little dance before, yes? Use the previous answer to find this. So it's going to be 150,000 times T. Is T2? How do I convert hours to seconds? You're saying there's 60 seconds in an hour? I think it's 60 times 60. I think it's 3,600 seconds in an hour. Yeah? So I'm going to take the shortcut and just do that. That's why there's a 2 right there. Thank you for making me feel better. Ah! You know what? I just did that so my Thursday afternoon block just jumped right now. So I apologize to my Thursday afternoon blocks. We'll see how loud the TOC has the video on. Crank it really loud, dude. What do you get? Let's crunch this myself, Mr. Duke. 150, 123 times 2, Brian, times 3,600. Oh, wow. You get a 108 and how many zeros? You know what? This is the time for scientific notation. I'm going to write this as 1.08 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Times 10 to the 9th, is that correct? Some of your calculators might have defaulted to scientific notation on that big a number automatically. They did, and so I'm right, yes. Power is measured in watt. Watts. Is this? No, this is work. Because W here is work, not power. So this one is going to be in joules. I've gone on my rant about how we really need more letters in our alphabet. Maggie, what C you want me to find?
Energy wasted.
Wasted. Oh. Okay. They've told me the efficiency. I haven't used that. This is very similar to the question we just did. I think the efficiency is going to be energy out divided by energy in. I think I want to figure out, first of all, how much energy we put in. How would I get energy in by itself? Where is the energy in right now? On the... So, times it, and then I can divide by the eta, the efficiency. So, energy in equals energy out divided by 0.18. So it's that number divided by 0.18. And I get a 6 with 1, 2, 3, 4, 5, 6, 7, 8. I get 6 times 10 to the 9th, which is not the answer. Cole, can you read me part C again? It didn't say how much energy did we use. It said how much is wasted. What are you typing on your calculator right now, Cole? I think the wasted part is whatever is missing. So now if I take this and I minus 1.08 times 10 to the 9th, here is how much got turned into sound and heat, which are the two primary ones. And I get 4.92 times 10 to the 9th. Which is also 72% of the energy because it's only 18% efficient. I threw a lot at you there. Efficiency is both really simple and really tricky. It takes some to wrap your brain around, and I recognize that. I'm not going to be asking you a gazillion of these, but we'll be using this terminology quite a bit as well. So what can you try for your homework? I think number 1 is good. 2 is good. Four is good. I skipped 3. Five or 6. Let's do 6. 7 is good. I'm going to skip 8. 9 is good. 10 is good. 11 is good. I'll do 12 and I'll skip 13. 14 is good. And 15. That's a lot. Wow. 1, 2, 3, 4, 5, 6, 7, 8. Oh, it's 11 questions, and you got 15 minutes. That's not too bad.